Again, we have a really interesting session for you. So this session we will kick off with Rene discussing the use of atomic scale modeling to advance battery technology. And I think it's a very unique contribution to our program because it takes a more of a sort of modeling approach to battery development. Then we'll hear about sodium all solid state batteries. And then we'll hear about sodium beta aluminum electrolytes. And finally, we have a contribution about potassium ion batteries. And I think that's also the only contribution in the program about potassium ion battery technology. So, yeah, without any further delay, I'd like to invite you to start your presentation. But just one note to the audience again, keep your questions coming. Again, I can't say this enough, but we absolutely love your questions. So keep them coming. And Rene, good luck to you.
Thank you very much, Kasha, and welcome everyone to the presentation. And yeah, as Kasha mentioned, this is, I think, rather an exotic topic. It's about modeling, and I try to convince you that this modeling that we apply or the techniques we apply basically help to advance battery materials and also understand. I think the key is here to create value to your approach to design new cells, and you can apply this approach based to all active materials in the battery cell, cathode, anode, electrolytes, and also the electrode-electrolyte interface is quite important because here this determines also the performance. So kind of a summary. So the industrial challenges I think is all known to everyone, and we try to basically also contribute with industrial and academic partners to improve existing battery cell technologies based on lithium ions or liquid electrolytes, but also to establish a next generation lithium ion cell technologies and technologies beyond lithium ions. And presumably the majority of you agree that the cost-effective R&D strategy with a minimum of trial and error is necessary to gather a comprehensive understanding about materials properties and the behavior and of the interactions of the materials during cycling. And based on our experience that we gathered in the last 25 and more years in the modeling activities and with more than 150 conduct research projects with industrial partners, we definitely can underline that the modeling can create value to R&D activities, especially in cases which experiments and measurements are difficult, costly, and time-consuming. Also, atomistic modeling provides views and insights complemented to experiments. So in general, you can think that experiments, just conducting experiments only, is like clapping with one hand. And the same is true basically just for doing modeling. You need both. In our modeling activities, we are applying multi-scale approach that bridges lengths from nanometers to micrometers and nanoseconds to even days. And I want to illustrate in a multi-scale approach with two case studies that are related to polymer composite electrolytes and the microstructure time evolution of metal electrode solid electrolyte interface. So this is a small overview. So I also want to introduce a bit the company Material Design. Also want to highlight the material challenges. So especially now this is focused on the charge carrier transport and the electrolyte composites, and also bridging the gap, as I mentioned, from atomistic scale simulation to microscale modeling. So Material Design is a company that exists since about 25 years, and we have about more than 700 institutions worldwide that use our software and also our services. Our mission is basically creating engineering value from materials simulations for engineers and also materials researchers. We offer Medea software, which is a simulation environment that we also use in our contract research projects. So basically, we apply as a service contracted research projects and also sidewise a bit consulting when it comes to when you want to apply our software or another software. We are globally present, so we have headquarters in the US and in Europe, but we also collaborate with business partners worldwide and also industrial partners. And our key expertise here is computational material science, chemistry, and chemical engineering. What I also want to stress is this tool that we develop, our service, is not only applicable to batteries. You see here quite some industrial areas in which our techniques or methodology also applied comes to metal and alloys, fluids, molecules, glass and ceramics, and even the nuclear industry, if you're interested in that. So you agree also that the battery cell is quite of an electrochemical reactor. So even if you put the components, individual components like the current collector,